substitution reaction of carboxylic acid derivatives. We're talking about this is a nucleophile and this is carboxylic acid, so this is OH. This one is OH. As far as the nucleophile text here, there's OH next step please, but here it's just addition. This nucleophile comes here and asks this double bond that you have to give one electron, which is pi electrons. These two pi electron form one bond and goes on oxygen. You see here negative charge on oxygen. This is addition of nucleophile here. After the addition of this nucleophile, the next step is that this oxygen has two electron comes down, form a double bond, and this OH group leaves, which is now elimination. And nucleophile like this form the bond here, and this is OH, which is leaving. Tetrahedral intermediate, this one is. Now if I talk about substitution and the sp2 hybridized carbonyl group implies this is sp2 hybridized carbon because it has three other atoms, oxygen, OH and R. Substitution at the sp2 hybridized carbonyl group implies a two-step addition elimination. Two-step, first step you have seen is addition, the second step is elimination sequence as shown above. So addition and elimination sequence as we have shown you above. This is another reaction. You see this is alkyl halide, alkyl chloride on the top. You see what happened with this alkyl halide if you put water on it, just a water, see what goes, what happens. You put water on it, you get alcohol. Very slow reaction. This chlorine leaves and OH form a bond here, but very slow reaction. Substitution and sp3 hybrid carbon. This is sp3. This is sp3 as well. This is ether. Even to put sodium hydroxide, nothing happened. No, nothing happened. You don't get here like this OH. You don't get OH, and this OR doesn't leave in the form of alcohol. No reaction takes place. Why this is going on, we will explain later. Here alkyl chloride, this is alkyl chloride, and you put water on it. As far as you put water, you can convert this alkyl chloride into carboxylic acids. This is a very fast reaction and substitution at the sp2 hybridized carbonyl. This is sp2 hybridized carbonyl, and this was sp2 hybridized carbon. This is carbonyl. So see the fast reaction. This reaction is pretty fast. You have a carbonyl and chlorine, and you put a water on it, and you get carboxylic acid HCl. This is very fast reaction. This is now ester again, but what happened to this ester? What happened to this ester? If I show you what happened with this ester, you put sodium hydroxide and this OR. What you get here, R leaves, and you instead of R, you get another sodium ion. So this is the only difference. R is leaving, and you're getting another plus charge species, which is no sodium. And what happened with this R? This R, other counterpart of the sodium hydroxide, which is OH, form a bond with that one, and you get ROH. Occupied at room temperature. This occurs at room temperature. Sorry. So what's this? Relative to substitution at an sp3 hybridized carbon. So what have you seen? sp3 hybridized carbon substitution is slow. The two-step addition elimination scheme of carboxylic acid derivative is more facile. That is slow, lower energy barrier due to replacement of the negative charge in the intermediate on an atom of higher electronegativity oxygen. So we're talking about replacement of negative charge, which is this oxygens, and higher electronegativity due to replacement of the negative charge in the intermediate on the atom of the higher electronegativity oxygen. Now we show this reaction. This is a peptide chain, And nature frequently implies carboxylic acid derivatives. Nature, you will see the carboxylic acid derivatives. Since these bonds are relatively easy to form, to cleave, enzymes can catalyze both processes. Since these bonds are relatively easy, they're very, very easy to form and cleave. They can form and cleave pretty easy. Enzymes can catalyze both reactions. Peptide, so this is a peptide chain of amino acids. This is peptide chain. What you see here is this is carboxylic acids, carbon, oxygen, O. This is not one proton because that proton has deprotonated, and you see this is the CHR and then NH, one amino acid, and other is again carbonyl and CH and NH, another carbonyl CH and NH, another carbonyl CH. So you will see carbonyl and then CH and something with CH, and at the end you will see here's amine. So on one side you see carboxylic acid, on the other side is amine, but in between them is like this NH and carbon oxygen NH, which is amide, and CH2 as well. So these structures of every amino acid. You see NH here, because this NH is in between, so it's not NH3, but outside is NH3. And you will see always here carbonyl between NX to NH. So CH carbon oxygen double bond NH, and then again CH carbon oxygen double NH, and then again CH carbon oxygen double bond. But here you see C. This is called C terminal. C terminal because this is carboxylic acid sites, and this is N terminus is amine site. This is polypeptide chain we're talking about. What you see here is amino acid 1 and amino acid 2. You see this amino acid is carbonyl group, and OH, this is carboxylic acid. And you see another carbon which has one R and another proton, and this is NH2 amine. And there is another amino acid is same, it has amine NH2, one carbon with R and H, and this is also carboxylic acids. So what happened? Two amino acids condense with each other. Peptide bond, how is formed? This nitrogen of one amino acid form a bond with the carboxylic acid for other amino acids. What you don't see here, you don't see this one as a protonation. This just leaves, and you have one proton less here because there was two protons, but you don't have one proton light, and you don't have this OH. So this forms the water, and what you get is now NH2 carbon with RH and carbonyl and NH, and carbon with R and H and carboxylic acids, and water is leaving here. This is dipeptide, two amino acids. They are reacting with each other. This is mechanisms was going on. This is mechanisms. You see, this is one amino acids. If it is this is carboxylic acids, you have O negative charge here in form a bond with phosphate, and this. These electrons just go with these all phosphate group, and this is phosphorylation. So you just got formation of bond like this. Here you can see here, this is called phosphate. What you see here is this OH also form a bond like this, and this all things can leave. This is a pretty complicated reaction. We go something easy busy. This is again OH and forming a bond here, right? And this O forming a bond. Okay, so what is this? This is alkyl chloride, acyl chloride, right? And H2O fast. This is anhydride, carbon oxygen O, and other carbon oxygen are. To these groups, carbon oxygen are in between them oxygen. This is anhydride. If you take anhydride, put in water, this is you get a carboxylic acids. So you get H here and two molecular carboxylic acids. This is acyl chloride. If you put water again, you get OH. And this is also ester. If you put a water acid, you again get this one H. These are different reaction how you can form a carboxylic acid. You can also form carboxylic acid from amide, put a water heat, and you get OH. So how you can form carboxylic acid? From four things. One is acyl chloride, putting water, pretty fast reaction. Other thing is from anhydride, which has two carbonyls group, and between them and oxygen, put water here, you get carboxylic acids. From anhydride, and this is from ester, you put water heat, you get carboxylic acid again. This, and from amide as well. So you get carboxylic acid from four things: chloride, from anhydride, from ester, from amide. So if carbonyl, everything has a carbonyl, but one is amine. So amine leaves and you get OH. Who is asking this amine group to leave or forcing water and acids? You have ester, you have OR group, and oxygen. Again, oxygen and R. Here is OH. So OR. R is more electron rich. So if something is more electron rich, can it leave easily? Why you think? Which is going to stable? Is the OR good leaving group or OH? Why you think? In acidic media, what will happen? The more basic thing will leave. So NH2 leaves, OR leaves. And here this oxygen on both sides, same groups. So they can easily leave. Both are stable. There is oxygen. Delocalization of electron. This is chlorine. Chlorine can leave and you get OH. Now this is you see is X, and you put a water, you get carboxylic acid. This is acyl chloride. You put ROH, you get OR. So just whatever is negative comes here. This is halogen, X leaves, then whatever is that comes here. Okay, so if you put a water, OH comes here. If you put alcohol, OR comes here. If you put ammonia and acyl chloride, NH2 comes here. If you put lithium, then you get OH here. This is and here what happened, RMGX. So what is another negative thing? R. So R come here. Now we show you another reaction. This is acyl chloride, and you react this one with amine. What can happen? This amine react here. Chlorine leaves and NH form a bond here. Now again, this is mechanism. If you see the mechanisms is the same. I think we went back on a slide, so we're going to look for some easy reactions, easy busy. Okay, pretty easy reaction. This is one reaction. You see, this is an ester and OH base. It's a nucleophile, form a bond here, O negative, and this group leaves, and what you get here is OH, which is carboxylic acids, and there is another OET which you get from here. This picks up this proton, and you have O negative, right? So what can happen? We finish it.